My name is Ruslan Bukin. I'm a FreeBSD OS developer working in the University of Cambridge Computer Lab. So my goal for today is to get you introduced to FreeBSD OS port to RISC-V architecture. And so I plan to start with a short overview of the FreeBSD OS, as probably not all the people here are already familiar with that. And then we talk about porting a bit, and I describe the current status of the port, and I describe the changes we propose to architecture. So let's start. So FreeBSD is an advanced operating system widely used in research and commercial space. FreeBSD based on version 4.4 of Berkeley software distribution, and now is most widely used BSD distribution. Unlike Linux, FreeBSD is a complete system. That means that both kernel and user space are delivered in a tightly integrated way. That means that both kernel and user space and libc and bin shell, they are all developed by the same people, allowing integrated development. Means that you can upstream the OS port to exactly one place and allow the parts to co-evolve. So let's talk about FreeBSD users. So lots of companies using FreeBSD. Say, as a general purpose system, it is used by WhatsApp company. A few years ago, they reported that they serve more than 1 million active TCP connections per server. And Netflix using FreeBSD serves 1/3 of North American internet traffic serving video, streaming a video. As an appliance OS, FreeBSD used by EMC company, NetApp, Juniper Networks. As an embedded OS, it's used by Sony PlayStation 4. And as an OS foundation, it's used by Apple. Micro 6 is based on FreeBSD, and they use our network stack. Open source community is much larger than this, with thousands of committers and hundreds of committers and thousands of contributors. So we support modern architectures like AMD 64, of course, and we're proud of our support of ARM7 processors, with lots of implementations by Altera, Freescale, Samsung, Exynos, and Xilinx, and lots of other companies. Last year, we added support for ARMv8 processors with implementation by AMD. So AMD servers based on ARMv8 architecture now can be powered by FreeBSD. We support 32 and 64-bit on MIPS and PowerPC as well, and we're now adding support for RISC-V. It will appear in next release, FreeBSD 11. So let's talk about the reasons to use FreeBSD. Of course, the main reason, the main obvious reason, is BSD license. Using FreeBSD with RISC-V, we can get a fully BSD licensed hardware-software stack, giving us an easiest path for technology transition, and we can distribute our code with partners easily. And FreeBSD has integrated build system, allowing us to build both kernel and user space just into commands. And we have interesting research tools like dtrace for dynamically tracing the kernel ported from Sun Solaris. And we have a framework for performance monitoring counters, and NetMap, a networking framework for fast packet inputs/output in user space. Of course, we support Latin-3 for describing hardware, to have a hardware description in a human-readable format. And the main file systems is UFS2, And we have enterprise class ZFS file system in 3. We also have a special application for U-boot called U-boot loader, allowing to boot FreeBSD in an advanced way from the U-boot, like say access UFS file system from U-boot, which is really useful. We support 2.5 for V8 and for x86, and we have a strong code style requirement. That means that no one allows to commit code that is not looking great to FreeBSD. This is my most lovely feature, that all the code in FreeBSD is really easy readable and understandable. So let's talk about porting a bit. The only tools we needed to port FreeBSD to RISC-V is very simple tools like objdump, elfdump, and hexdump. Objdump is used to see the sequence of instructions in kernel and compare it with the output of simulation tool. Elfdump we need for runtime linker, and just a couple of times I used hexdump to write a driver for HTF block device. And of course we need a simulation tool. We actually have no much choice here. The only Spike supports modern version of RISC-V. And I just here want to say personal thanks to Spike developers for that great simulation tool. I really like. I don't like not free software, so QEMU is not really a great choice, I think. While Gem5 is free, but it is too advanced and lacks of simple features. And while Spike is really simple and it is really fast, it boots FreeBSD just 1 second to single user shell, and about 10 minutes requires to boot FreeBSD to a multi-user. RISC-V designed it to have a special privilege level machine mode. And one thing that surprised me is that console device and other HTF devices can be only accessed from machine mode. So that means we have to switch to machine mode every time we want, say, to put chart to the terminal. That is a bit strange, I think. And while interrupts from machine mode are always enabled, and we can't handle interrupt in supervisor mode any given time because operating system can disable interrupts for some critical sections. That all means that we have to collect events somewhere in machine mode, like in memory, and allow the operating system to read that events later when it have time for that. I understand that machine mode is designed actually for firmware or for bootloaders, but I wanted to write it, to implement it in FreeBSD just like for better understanding of architecture. So when we start porting, we usually start with early assembly code. We need to put hardware to some known state, like we need to disable MMU and like reset some hardware configuration. And we need to build a ring buffer for events. I described it on previous slide. And we need to build initial page tables covering the size of our kernel, like 3 or 5 megabytes. Once we build the initial page tables, we can enable MMU and branch to virtual addressation, exit from machine mode to supervisor mode. Once we get a supervisor mode, first thing we need is working printf. FreeBSD has a special way for working printf very early, to have printf very early. And we need here to implement just a simple function that takes an argument with a chart to print. And in case of RISC-V, it should switch to machine mode, print character, and return back to supervisor mode. And then we need to implement lots of atomic functions because most of FreeBSD subsystems using atomic functions. And my initial fault was that I implemented atomic functions, but I did not test that. So that was really hard to find bugs in that area. And once I realized that, I re-implemented all of the atomic stuff and tested it well before using in FreeBSD. And we then need to initialize virtual memory. And the first thing we need here is to provide information to VM subsystem about physical memory regions. And here I haven't found any way to get the information from hardware. So I just hard-coded at this step 128 megs in FreeBSD. Probably the best way if RISC-V will provide that, or alternatively we can use flattened device tree for that information. And we need to work on machine-dependent part of VM subsystem, call it pmap in FreeBSD. I'll talk about that a bit later. Once we get some VM working, we need to handle VM traps, so we need to work on exceptions. And once FreeBSD go into boot, we need to work on context switching, because almost every FreeBSD subsystem creates a thread, and we need to switch between them. And of course, we need working on timer and interrupt control driver. FreeBSD requires at least 2 timers, free run timer and event timer. And it looks like RISC-V provides just 1 timer, which is really strange. I think like any kind of general purpose system should provide many, many timers, because they are very useful. And we need to work on lots of functions to copy data between kernel and user space, like fetch user byte, store user byte. There's lots of assembly functions we have to implement before we go into the next step. And once we get all of this, we can try to compile bin shell statically, because we don't have any runtime linker yet at this step. And we can put it to memory disk, or we can write a shift block device driver. I started with memory disk. And signals is the last thing we need, because even bin shell don't requires implementation of signals, but other shells like binc shell requires. Here is a simple example how we handle traps in machine mode. And so we have to set up vector, and vector for supervisor trap. Once we get a trap, we look the cause of trap, and in case it is interrupt, we must handle it in machine mode. And if it is a VM trap, we can redirect immediately to supervisor mode, to CPU exception supervisor. And of course, we need to change stack pointer once we get machine mode trap, because we can't use MMU. MMU is disabled in machine mode, and so we can't use stack pointer from supervisor mode or from user space, because they have a virtual addressed stack pointer. Here we can use only physically addressed stack. So once we get a supervisor mode in assembly, we do standard things like save registers on stack and call in C function in kernel do trap supervisor. In case of user trapped, we must switch stack pointer also here, because we can't use user stack pointer in kernel. So pmap is the most sensitive machine-dependent part of VM subsystem. There is about 40 functions to implement, like functions callbacks. VM do call when it wants to insert page tables, or removing page tables, extract information from inserted page tables, protecting page tables for copy on write functionality. And I would say this most hard things in porting. Like implementation for RISC-V takes about 3,000 lines of code. For example, implementation for AMD64 takes 7,000 lines of code in a pmap. Here's a simple example how we do context switching. Context switching in FreeBSD is really, really easy. We just need to implement machine-dependent function CPU switch, which takes 2 arguments, old thread and new thread. We should just store information of new thread to per CPU object of current core. We should store all registers to old threads program control block, switch pmap, and switch page table based register, and restore register from a new thread. So it's kind of very easy. I spent just like a few hours for that. In user space, first thing we need is to compile gmalloc. Gmalloc is a memory allocator FreeBSD use, and there are some if-defs we have to implement for RISC-V architecture. And then we're working on C startup code like 31.30n. That code will be embedded to each binary or library. In libc, we need to work on syscalls and standard Unix things like set jump, long jump, set thread pointer. We also should take care about floating point operations. I haven't found that Spike supports that, so I enabled softcore at this step. And of course, we need to work on the runtime linker to get working binaries that is linked dynamically. This is the most hard thing in user space. So pmap is most hard thing in kernel, while runtime linker is the most hard thing in the user space. And it's twice or 10 times harder to work both of them same time. Here's a simple example of syscalls. Syscalls is very easy. Just in a few instructions, we can produce the syscalls from user space, just like we said that a syscall ID to temporary register produce environment call. In kernel, we should, in exception handler, we just call a machine-independent function, syscall enter, pass in a frame. And we only need another couple of functions. So FreeBSD kernel knows how to take arguments from a frame and how to set return value. And it is like nothing else we need to implement syscalls, just a couple of functions. Here's interesting facts about FreeBSD RISC-V port. We based our port on ARMv8, which is really great, simple, and really understandable. And our diff is about 25K lines. We edit or modified about 200 files in a 6-month period. And here I want to say thanks to Robert Watson for organizing that project, and the folk from University of Cambridge, and David Chisnell and returner. Many thanks to Aaron Thomas for help with toolchain, and Edmus T from the FreeBSD Foundation. We started in August last year, and we get kernel working just in 2 months, and user space take another 1 month. We're now committing support to FreeBSD main repository, and we have lots of interesting plans for next year. So we already committed C startup code, machine headers, about 60 files, and we committed runtime linker. We need to commit, and we plan to do that in a few weeks, rest of user space, kernel, and libc. Lots of plans for next year. We want to work on SMP, symmetric multiprocessing, on just multi-core. I noticed that Spike do support that, and we plan to work on FPU if any of simulation tool or FPGA will provide that. And TLB cache is also important. I plan to write the driver for HCF as a RAID device, and we need to increase virtual address space because current implementation of GNU toolchain only supports like 3.5 gigs of virtual addresses, which is really small, even for 32-bit system. But no, it's okay for 32-bit system, but for 64-bit system, it's kind of really small. Hopefully, it will be fixed in maybe LLVM toolchain if anyone working on that. Yes, we plan to work on FPGA implementations. We want to support low risk, of course, and other FPGA stuff. And it will be really fun if some of the 32-bit RISC-V implementation will do support MMU, because I have not saw that we have any 32-bit with MMU. Probably that scale don't support MMU. And of course, the trace and counters, QEMU, and we need to remove machine mode code looks like we need to remove machine code because it's designed for bootloaders. And we have about 25,000 of ports collection in FreeBSD 3, so we need to able to compile that and to run that. One of the change we propose is to split supervision page table registers to 2 registers. As I said, we based our port on ARM v8, and I noticed that in ARM v7 and ARM v8, both they have 2 registers. One for user virtual addresses and second one for kernel virtual addresses. And this this allows us to have a code that looks great. Like if you need to change page table register each time we change in privilege level, it will be a bit mess in the code, because like kernel uses its own page tables, and each process has its own page tables, and it will be really big mess if we will do that anytime change the privilege level. So we already committed that in our branch, and we use a split page table based register. So in case of split page table based register, MMU worker just should see topmost bits of kernel of virtual address, and if it is kernel address, it should use super page table based register 1, and in case of user space, another one page table based register. Thanks. Here's information about project.